Chapter 9, Fire Protection Systems. Again, it's important to note that this is just an overview of fire protection systems, and we'll go more in detail on fire protection systems in another FRSC class. Your objectives: define the two sources of water supply. Describe the four components of a water system. List and describe the two categories of water supply systems and explain the advantages and disadvantages of each system. Explain the different types of pressure. List and describe the three basic types of water supply system. Identify the three components of the water distribution grid. Identify and describe the three types of fire hydrants. And describe the various types of sprinkler systems. Understand the various types of detection and alarm systems. Describe the various types of special fire protection systems. List and describe the different types of extinguishing agents used in fire protection systems. So let's look at the different types of water in terms of how we get it. First being subsidence. And this is just an example of a groundwater subsidence, so something coming up from the ground like natural springs and things of that nature. Next, you have watersheds. And watersheds are basically rainwater that flows into your creeks and rivers and on into your lakes. So let's look at the water system components. And the first we're going to talk about are gravity systems. And what we're talking about here is how is your water system pressurized? And there are three different types, really two. One is a combination. And the first one being is a gravity system. So the water comes from either elevated towers or from a pumping station high above the town. And then the water leaving that object or system develops something known as head pressure, and that is the amount of pressure that the water produces from going downhill by means of gravity. And this is used to pressurize the system, which allows the water to get transported from its starting point into the end user or where your faucet is. The gravity system is the most reliable distribution system. Here's an example of a water tower. And of course the water comes out of the bottom of the tower and pressurizes the system. It also uses a small pump during the off-peak times to fill the tower so it can pressurize the system. The other type of system is a direct pumping system. In the direct pumping system, the water is treated at a processing plant and then the system is pressurized through a series of high-powered turbine pumps that move the water from the distribution system, from the plant into the distribution system and on throughout the grid to the end user. The third system is a combination, and it uses gravity and pumps to supply the system. Again, here's another picture of a water tower that can be used to help pressurize the system by means of gravity. So let's look at the different components of the water system. First, you're going to have the water treated. So any public water system must have means of being filtered and purified so it can be used for consumption. The vessels may collapse and subject to systemic or extreme environmental forces. Here's a picture of a water treatment plant. After the water leaves the water treatment plant, it goes into a system of grids that distributes it out to the users. And what you have are primary feeders, secondary feeder mains, and distribution pipes. And what these all do, it goes from larger to smaller to the end user. So here's a good picture of how the grid system works. You have the primary feeder, And notice how this is a square. In most water systems, they intend to be a loop. That way you've got water coming in from more than one direction. So if you have something that breaks, whether a pipe or say a fire hydrant gets knocked over and they have to shut a section off, you're not totally taking down the entire system just because of an issue. When you're looking at the pipe size requirements, it can be anywhere between 6 and 12-inch pipes, depending on what part of the system it is and the water consumption demand of that area. And the way they decide, it depends on the flow rate or how many gallons per minute is being used. So the formula they use to determine the flow rate of a particular size area is the large diameter pipe square divided by the small diameter pipe square, and that gives you a flow rate in gallons per minute. One thing to keep in mind with these pipes, even though they're part of the municipal water system, the internal diameter can be shrunken due to the three following phenomena. One is tuberculation, and this refers to a formation of corrosion that makes mounds in the pipe, thus reducing the diameter. Incrustation is very similar, as it is a collection of calcium and other hard water deposits that again start narrowing the circumference of the diameter of the pipe. And of course, sedimentation is the settlement of dirt and other impurities that make it into the water supply system, and then they ended up encrusting the bottom of the pipes, again also shrinking the diameter. A lot of times the sedimentation occurs at the end, or a line that only has water flow coming in from one side. Other important things to consider when you're talking about your water system. You have something known as residual pressure and static pressure. Static pressure basically refers to the pressure in the line when no water is flowing. Residual pressure is the water left in the line after water is flowing. While conducting flow tests in your district, you find a hydrant that has a static pressure of 85 psi, meaning nothing is flowing. It has 85 pounds per square inch pressure. But when you open the hydrant valve, the residual pressure drops to only 40 psi. What information should you seek, and how will this situation affect you and your fire crew? So what they're trying to point out here is 40 pounds per square inch is not a lot of pressure on a hydrant that's left, meaning you can't flow a whole lot of water. Now, things to keep in mind is there a problem with the pumping system? Is there a problem in terms of the amount of water available in the system? Or is this during some sort of peak water usage time? Essentially, everyone's home, they're taking showers, washing their clothes, and flushing their toilet all at the same time. If not, and this is just your average pressure, then you're going to have possible water issues if you need to use that particular hydrant to fight fire, because your gallons per minute are going to be extremely limited. You have a couple of different water systems. For example, in San Francisco, they have two water systems. One is for drinkable water, and the other is just for what they call non-potable or non-drinkable water, and that's used for construction as well as fire service in terms of firefighting. The other type is dual, meaning it's used for both. Most people here in Georgia use a dual system, meaning that all the water is potable or drinkable type water, and it can be used for firefighting, construction, or drinking. So look at your hydrants. Your hydrants have a couple different types. First one we're going to talk about is a dry barrel hydrant. This is the most common used in the fire service. It operates by turning a nut at the top of the barrel. One disadvantage is the hydrant must be shut down to add more hose lines off that hydrant. Essentially, this hydrant has no water in it until after you open it up, and then the water comes up from the ground, charging the hydrant, and then after you close it, the water seeps out through a weep hole. This type of hydrant you find in areas that are prone to freezing. Here's a picture of a typical base valve dry barrel hydrant. The other type of hydrant is the wet barrel hydrant, and this has pressurized water in it at all times. It does not require a base valve because this area that they're in is not subject to freezing temperatures. Something that's what they call it California, so Florida, basically areas that don't freeze. Notice the difference between the wet barrel and the dry barrel in terms of look. Here's a lovely picture or graph to illustrate the difference between the dry and the wet barrel. And then notice again on the wet barrel how that water stays beneath the ground or beneath the frost line to prevent freezing. Third type of hydrant is a dry hydrant, and that's found in rural areas. This is a non-pressurized hydrant system that's installed at a static water source, meaning lakes and ponds. The fire truck basically pulls up to this connection, blows some water through the system here to clear out any debris, and then begins to take on water till it's full. Hydrant maintenance and flow testing needs to be done either by the fire department or the water department or a third agency. And according to NFPA, they should be visually inspected every month. They should be lubricated twice yearly, and that should be with some sort of food grade type oil. And what they want lubricated is the bonnet on top and the couplings on the side. You should open and close the valve yearly, and they should be classified in terms of color coded based on their flow rates. When you're looking at the hydrant maintenance, you need to be mindful of the static pressure, the residual pressure, and the flow pressure. By getting all three pressures, you can come up with the hydrant flow formula in terms of gallons per minute, which is 29.7 times the diameter square times square root pressure times the coefficient, and this is just a set number based off the hydrant openings. I don't expect you to remember it until we get into fire department hydraulics, which is another class. NFPA 291 recommends hydrants be color coded and classified. Jurisdictions may use their own color coding system. NFPA recommends the distance between hydrants be less than 800 feet, with target areas, meaning special hazards, at less than 500 feet. Another type of system to keep in mind when we talk about fire protection is a standpipe system. And standpipe systems are divided in different classifications, and a standpipe is essentially something that has water on it, or it's just a pathway to get water from the ground level to interior structures that are probably more than 2 or 3 feet or 2 or 3 stories in height. A Class 1 system should only be used by firefighters, and one or more 2.5-inch hose connections are required. The water supply from outside the building is done by the fire truck. Often you see these Class 1 systems in parking type decks. Here's an example of a Type 1 standpipe system. A Type 2 system is designed for use by building occupants, and it should have an 1.5-inch hose and nozzle provided with the standpipe, and it should be found in some sort of wall cabinet. Here's an example of a Class 2 system. Now, they don't recommend that firefighters use a Type 2 standpipe system. Reason being that hose and nozzles are usually far less than what is required for adequate water flow to put out a room and content fire. Also, there's no guarantee that the nozzle or the hose has been tested on an annual basis, which could lead to failure. So with that information, what they really would like you to do here is bring up your own high-rise pack and connect your own hose and nozzle to the standpipe and use that to fight the fire rather than the one that is already there. Your Class 3 system is a combination of Class 1 and 2. Both should have a 2.5-inch outlet and an 1.5-inch outlet with pre-connected hose and nozzles that are in place. Also to note, with the different types of systems, the amount of gallons per minute they have decreases as you go from 1 to 3. Now there are different types of standpipe systems. You have an automatic wet system, meaning that water is on it 24/7. You have an automatic dry system, which means that the system itself is dry, but once the air evacuates out of the tubing or the standpipe, then water begins to flow. Then you have a semi-automatic dry system, as well as a manual dry system and a manual wet system. And those three at the bottom basically require some sort of switch or some activation process to get water to come out. So the automatic wet system is the most common. The piping is filled with pressurized water from a water supply, immediately available for firefighting operations. The dry system is used where areas are subject to freezing temperature, and again the pipe is filled with pressurized air. The semi-automatic dry system is just used where areas are subject to freezing temperature. It is filled with pressurized air. There are remote devices activated at the hose station where the air is expelled and the water fills the piping. The manual dry system. This system is not connected to a permanent water supply. It's filled with air at normal air pressure. The water filled from the fire department connection that is being powered by the fire apparatus will expel the air from the system and apply water to the entire system. The manual wet system. This system is not connected to a permanent water supply. It's filled with water from the domestic water supply line. The water supplement needed from the fire protection comes from the fire apparatus. So essentially it has some water on it from the residential system, but not enough to do the job. So the fire department needs to supplement it with water coming from the fire truck. So now let's look at the flow rate requirements from the Class 1 to the Class 3 system. 500 gallons per minute from the first standpipe and 250 gallons per minute from each additional standpipe, with a maximum of 1,250 gallons per minute must be maintained at a flow rate for 30 minutes. Residual pressure of 100 psi while flowing 250 gallons per minute at two topmost outlets, plus 250 gallons per minute from each additional standpipe up to a maximum of 1,250 gallons per minute. Again, it's important to note that these standpipes operated on multi-floor structures. The minimum flow pressure of 100 psi to each outlet is required for Class 1 and 3 system. A Class 2 system only requires 100 gallons per minute for 30 minutes and a residual pressure of only 65 psi while flowing. If the building is 100 feet or less, the standpipe riser must be a minimum of 4 inches in diameter. If the building height exceeds 100 feet, the standpipe riser must be a minimum of 6 inches. The top 100 feet, however, can be reduced to 4 inches. So let's look at the Class 2 system. If the building height is less than 50 feet or less, the standpipe riser must be a minimum of 2 inches in diameter. If the building height exceeds 50 feet, the standpipe riser must be a minimum of 2.5 inches. If the building height exceeds 275 feet, it must be divided into zones, meaning that each zone has its own separate standpipe. So let's look at some pressure regulating devices. Head pressure is caused on the lower outlets at the height that the standpipe increases. Pressure reducing valves can reduce the pressure to 100 psi or less. There is no compensation for friction loss in the hose line. The early sprinkler systems were designed by John Carey in England in 1806, Sir William Congreve in 1812, Henry Parliament in Connecticut in 1874, and Frederick Grinnell and John Taylor. Sprinkler systems have been used for quite some time and have been quite effective in maintaining fires and keeping them in control. These devices have changed little since their inception. Here is a modern-day sprinkler alarm control valve. Sprinkler systems have sprinkler heads. Here is a picture of a typical sprinkler head. This sprinkler head has a fusible link, meaning something metal in there that you can see that will melt when the temperature in that room rises to a certain preset temperature, which melts the metal and causes an opening in the orifice of the sprinkler, allowing water to escape, thus being applied to the fire. NFPA report U.S. experience with sprinklers and other fire extinguishing equipment. 97% of wet pipe systems and 86% of dry pipe systems and 100% of other type systems can control or extinguish the fire with the activation of 10 or fewer sprinkler heads. This basically says to us that sprinklers work, and when they do go off, they use far less water and do far less water damage and are able to put the fire out while it's still in its incipient or growth stage. If you're looking at NFPA codes, the important ones to remember for your sprinkler systems have to deal with NFPA 13, 13D, and 13R. These standards reference code installation and requirements. These codes also reference inspection and annual testing requirements, as well as reference your standpipe systems and their testing requirements, as well as their requirements as a whole. Let's talk some about automatic sprinkler system and their components. First, they have to be supplied by water. The required minimum should be 6 inches in diameter, and they should deliver at minimum 15 psi to the highest sprinkler head. If designed by hydraulic calculations, residual pressure can be 7 psi. If using an elevated storage tank, it's required to be 35 feet above the highest sprinkler head. Again, that's being generous because it's allowing for gravity and head pressure to power the system as opposed to pumps. Your automatic sprinkler system should have a black flow preventer. And what this basically does is when your sprinkler system is hooked up to the public water supply, it should have a valve that allows for water only to flow one way into the system, and then no water should be able to leak back out into the municipal water supply. This is often accomplished by the means of using pressure and a valve. Here's a picture of a backflow preventer on a sprinkler system. Another component of a sprinkler system is a water flow control valve, and this should be located on the riser between the water supply and the fire department connection. And there are a couple of different types. The most common is an outside stem and yoke, also known as an OS&Y valve. This is classified as a gate valve. It is also an indicating valve. The position of the valve will indicate whether water is being supplied to the structure or not. Here's an example of an OS&Y valve. When you can see the threads here, it means that the valve is open and water is being supplied to the system. When you don't see the threads, then the valve is considered closed, meaning no water is being supplied to the system. There are two other types of water flow control valve indicators. One is a post indicator valve, often found in the yard. This sprinkler control valve is underground and allows for opening and closing of the valve. Another type is the wall post indicating valve, which is similar to the post indicating valve, but it's installed inside the building by an exterior wall. You can tell whether or not water is being flowed through the system by looking in this window here. It should say opened or closed, depending on whether the valve is open or closed. Here is a wall indicated valve. Again, here's your window, and it should read open or closed. A lot of times these valves are going to be chained in the open position as to keep from tampering. And then if the fire department or somebody needs to close it, then they just cut the chain or get a key to the lock. Post indicator valve assembly. It can be wall mounted or placed in line. It operates as a butterfly valve, a crank handle or wheel mounted on the side of the valve housing, which allows for opening and closing. Here's an example here. Another important feature of an automatic sprinkler system, it should have a FDC or a fire department connection. This is required of most sprinkler and standpipe systems, as we discussed earlier with the standpipe system. This is found on the exterior of the building or mounted as a manifold. This is where the fire department can hook up either 2, 2.5, or 4-inch lines to some pipe threading, and then they connect directly to the system. This allows the fire department to subsidize the sprinkler system and ensures that adequate water flow and pressures are being maintained while firefighting operations are going on. Here's a good picture of an FDC. All water flow control valves should have some sort of audible alarm when water is flowing. Here is a picture of a gong type alarm that may be operating when water is flowing from a system. Your sprinkler system should have three main components inside. You should have a riser, cross mains, and branch lines. Here's a picture of the riser. This is where the water enters the structure, gets charged into the system. The cross mains deliver water from the risers to different areas of the building, being protected from the system. And then finally you have the branch lines, and these are where the sprinkler heads are attached and the water exits the system upon sprinkler head activation. Your sprinkler heads have several dual purposes. They can either be system activated devices or heat detectors. Here are examples of your heat detector devices. They can have fusible links, as we said earlier, such as these, or it can have some sort of glass fluid-filled frangible bulb. And basically that fluid is designed to boil and expand at a certain preset temperature. And once it does that, it breaks the glass, again allowing for an opening in the orifice for water to exit the system. The sprinkler heads can come in different setups, meaning they can be the traditional pendant style. They can be upright or wall configuration. Their opening is between 3/8 to 3/4 of an inch, and depending on where they're mounted, will dictate which sprinkler head is used. Here are an example of all three. Again, I don't expect you to memorize this formula. This is more for your general knowledge. But a formula to calculate your sprinkler flow rate is Q equals K times square root of P. Q is the quantity of flow, meaning gallons per minute. K is the discharge coefficient based on the orifice size and surface characteristic, and P equals the discharge pressure at the sprinkler. Like your standpipes, your automatic sprinkler systems can be wet or dry. Wet pipe systems are installed in areas not subjected to freezing. Sprinkler activation, pressure surge, and retard chambers are all present. A dry pipe system is more complicated than the wet pipe. It's used where there's a possibility of freezing or the temperature goes below 40 degrees. They're usually pressurized with air versus water. In your wet system, they're pressurized with water and they just are waiting for some means to be discharged. In the dry pipe system, they're pressurized with air, and then once the air leaks out, then the water is allowed to go into the system. A lot of times your dry pipe system has some sort of jockey pump to help maintain the pressure in the system and prevents false alarms and premature activation of the system. And depending on the dry pipe system will dictate whether it's a single or double seated clapper, and that's just the device that it's used to hold the water out of the system until it's ready to be discharged. And of course, the disadvantage of this is the water is not able to charge the system until all the air has been purged. Now there are different types. One is a pre-action system. Now this is a dry pipe system where a pre-action valve and supplemental detection system. When the system senses a problem, it opens a pre-action valve and fills the piping with water. The practical system when water discharge is a concern. So a pre-action system, basically some fire alarm or some other triggering device goes off and it allows that valve to open up and charge the system. Now hopefully it's not a false alarm. If it is, now your system is charged with water. Another system is a deluge system, and this is traditionally a non-pressurized dry system with a detection system. This is used when rapid amounts of water is needed in such things as hangars or electrical transformer rooms or outside transform pads. The deluge system, essentially, the sprinkler systems are all in the open position. So when the water hits the sprinkler systems, it floods the area. Residential sprinkler systems are becoming increasingly popular in modern construction and buildings. They are, of course, popular with the fire service, but they are very controversial with some building contractors. They claim that the cost is prohibitive in putting these things in. But time and time again, we show them that reports show that these systems save lives and money in terms of fire damage cost and, of course, the cost of life. Often, residential sprinkler system unit contain an in-stream alarm switch that activates when water is being flowed through the piping. It is a fast response sprinkler heads are designed to direct water high on walls and to protect contents in the perimeter. Often these systems flow less gallons per minute than your traditional sprinkler systems found in businesses. There are 6 basic features. They have a control unit, a primary power supply, a backup power supply, a trouble single power supply, and one or more initiating device circuits, and one or more alarm indicating device circuits. So basically, it has numerous backups in terms of power, it has warning lines, and it has several different methods to activate the system. All signaling and detection components should be recognized by a testing laboratory such as UL or Factory Mutual Research Corporations. They should conform to NFPA 70 and NFPA 72 standards. When we're talking about our alarm system and we're talking about the devices that single, there's a problem here. You have the non-coded system. So when the control unit receives a detection signal, it is initiated through all audible and visual alarms throughout the property. The location of the problem is not identified. However, the alarm remains active until the system is reset. The local alarm system may also have a zone or non-coded system, which the property is divided into zones, so the location alarm can be determined at the control unit. So it'll say zone 1, zone 2, or zone 3 where the alarm is going off, which helps minimize the time required to find the problem or the source of the fire when fire departments arrive on scene. The master coded local alarm system. This system uses all audible and visual notification devices that are a normal part of the building operation. The system does not indicate the location of the trouble. The zone-coded local alarm system uses the same zone circuitry as the zone non-coded system. The coded audible circuit added to each zone circuitry at the control unit will help identify the location. Auxiliary systems. They notify the fire department dispatch office, and they can be activated manually or by fire detectors or water flow. They can also interface with a public alarm system. Remote station system. This system sends alarm notifications to fire department dispatch offices. This is often sent through telephone lines. If there are multiple properties, the system must be coded to identify which one is having the alarm. There is also a public safety answering point. Proprietary system. This is used to protect large commercial and industrial complexes, also found in high-rise buildings. The notification is sent to a supervising station on property that is manned 24 hours a day by personnel of the occupant who notify the fire department communication center. Central station system is similar to proprietary systems, except the alarm panel and supervising station is not located on the protected property. The not supervised by employee but by a contract or a service company. Heat detectors. They date back to 1860s. They are designed to operate when a predetermined temperature is reached, and they should be located on or near the ceiling as heat rises. The fixed temperature heat detectors are a spot type, such as we talked a little bit earlier, your fusible link, your frangible bulb, or a bimetallic type disc. Another type is a continuous line type and a thermal lag. The continuous line type is basically a metal that is insulated and runs throughout, say, a warehouse. And then when the temperature gets so hot, the metal inside that tubing will melt, breaking the connection, thus causing an alarm to go off. Problem with this type of system is the thermal lag time, basically the time it takes for the system to heat up and melt and activate prior to notification of first responders. Radarized heat detectors that will eliminate the thermal lag. If the rapid rise in the temperature exceeds 12 to 15 degrees per minute, the alarm will signal. Other types are combination. They use both rate of rise and fixed temperature principles. They contain air chambers and diaphragm that is held open by a fusible link. They can respond to both rapid and slow increase in temperatures to sound the alarm. These systems are designed depending on the occupancy type as well as load in terms of what is being stored in there. Smoke detectors. You have several different types. First being an ionization detector, and this contains a small bit of radioactive material that is used to ionize the air in the sensing chamber. Another type is photoelectric detectors, and that basically uses light obscured systems or light scattering systems. When the light is broken up or obscured by smoke particles, then the alarm will sound. Another type is a light detector or a flame detector. It uses infrared flame detectors, ultraviolet flame detectors in combination to identify the presence of fire and sound the alarm. Here's a picture of a flame detector. Another component of the system could be a carbon monoxide detector. NFPA 720 recommended practices for the installation of household carbon monoxide warning equipment, and it was published in 1997. In 2005, the recommendation was converted to a standard. Specialty systems. A Halon system. The system dates back to the 19th century. The Halon agent is referred to by first, second, third, or fourth digits, the number, and what's in there. Halon systems basically will displace the oxygen and suffocate the fire. The Halon systems were used in places where water is traditionally not recommended due to, say, electrical components such as computers or servers. Both systems are clean extinguishing agents. They do not leave residue after extinguishing the fire. The Halon 1211 is more toxic but has since been discontinued. You may still find them on some military bases. Carbon dioxide systems are similar to Halon systems. This is made up of gas. It is colorless, odorless, and non-conductive and non-toxic. It is non-flammable. Since carbon dioxide is 1.5 times heavier than air, it essentially pushes the air out of the way. You have two types of system, a total flood system, which is designed to fill the entire area, and then the local, which does not flood the area. They can be high pressure or low pressure systems. High pressure is stored at room temperature, and the low pressure is stored at 0 degrees Fahrenheit. Here's an example of a system flooding an entire area. These systems do require a preactive alarm to allow occupants time to evacuate the area. As it displaces the oxygen, it does have an asphyxiant quality about it. Another system is your dry chemical system. These are designed to extinguish flammable liquid fires, and they may also be used on electrical equipment. These are your traditional type ABC extinguishers. They are made by using various components of sodium bicarbonate, potassium chloride, urea potassium bicarbonate, or monoammonia phosphates, again, to be used to smother and put out the fire. There are 4 extinguishing properties of these dry chemical extinguishers. They can be smothering, cooling, radiant shielding, and they break the chain reaction. Now let's look at our wet chemical systems. They replace dry chemical systems for the cooking area, the Class K fires, because the dry powder doesn't have a very good track record on those type systems. Essentially what it does is saponification, meaning the chemical that's mixed with the cooking oils basically turns it into like a buttery gel substance that prevents it from igniting and staying on fire. Another type system is your foam system. This is effective against fires fueled by hydrocarbons. Foam will expand when mixed with water, and you have three different types: low, medium, and high. And that basically refers to how much bubble you're going to get versus water ratio. Foam can be a detergent base, known as a synthetic, or it can be a protein, which is made usually from plant or animal fat matter. There are 6 basic types: a self-contained apparatus system, a fixed system, semi-fixed type A, type B, high expansion, and foam and water system. They can also be compressed air foam systems known as CAFs. They can be fixed or self-contained systems, and basically they compress air which is forced into the foam solution. This uses less foam and less water. Here's an example of a foam extinguishing agent being used on a hydrocarbon fuel fire. To apply the foam, there are 3 basic methods: the roll-on method, the bang-down method, and the rain-down method. The roll-on method is essentially spraying the foam solution above the flaming liquid or the liquid to be covered and allowing it to essentially get pushed onto the fire. The banked on method would be, say, hitting a wall or something above or beside the flammable liquid and allowing it to run down that way. And then the rain down is essentially just like adding rain or snow, and you shoot the foam up in the air and you allow it to slowly drip down, covering the entire area. Summary: firefighters must know that firefighting needs of their jurisdiction and be able to identify and understand the equipment used in the building. Communities and their needs change, and firefighters must keep up to date. Okay, gang, so we covered a lot. Make sure you read the chapter. And if you have any questions, you can email me at aroberts@athenstech.edu. Until next time, be safe and have a wonderful day.